Okay, hi everyone. So this is my last lecture on prerequisites for the cutoff. So I'm going to talk about this Bakry-Emery notion of curvature, which probably most of you know. And again, this was invented 40 years ago to understand diffusion. It's a very powerful theory, as you will see. But we are going to use it tomorrow and Friday to understand cutoff. We are going to use it in a completely different way as what was done classically. Okay, so it's a notion of curvature just like the Olivier-Ricci curvature, and I actually conjecture that the two are related, so I will give you a precise statement, a precise conjecture for that, but as far as I know, there is no connection between the two that has been proved. Okay, so what is this Bakry-Emery notion of curvature? Let me first start with recalling our stochastic setup. So in our simple discrete state space universe, this generator is just a finite sum, like that. And you are just looking at how your function f evolves on average when you make a transition starting from x, right? That's the generator. Okay, so there is so that's the generator. There is another object that is a second order version of this, or a quadratic version of this, which is obtained by just putting squares here, and it's called the carré du champ. Okay, so carré du champ is this operator. It's a quadratic operator on f, and you just look at how much your function varies when you, but in terms of squares, when you make a transition. Okay. And for good reasons, there is a factor 1 alpha. Okay, so this is the generator, and this is the carré du champ.
Kind of a variance, no?
Yes, yes, exactly. This is local expectation when you make a move starting from x, and this is local variance when you make a move. Okay. Okay, so it's a quadratic form in f, right? So as any quadratic form, you can polarize it to get something that depends on two coordinates, right? So this is in fact gamma of ff, where the general definition is this. Okay, and again, I won't write gamma ff when f equals g, I'll just write gamma of f. Okay, so we have already seen this expression at some point. So let me remark this, it's important. You can interpret this gamma as a local Dirichlet form. In this very stupid sense that when you average, you get the Dirichlet form. So if you look at sum over all x, pi of x, and then gamma fg of x, what you get is the average of this, and we have seen that this was the Dirichlet form, at least in two cases. When your chain is reversible, so you can always assume this if you want, or when f is equal to g, right? We had seen that this Dirichlet form can be written in this symmetric way. Okay. So just view it as a local Dirichlet form. Okay, so this quantity comes naturally, shows up naturally. You know, this generator is the first order Taylor expansion, the first coefficient in your Taylor expansion when you want to understand the expectation of f of xt for t small. And this is the first order coefficient when you want to understand covariance of f of xt and g of xt. Okay, so it's a natural quadratic version of this. Okay, maybe an important, another important remark is that there is an abstract way to define this gamma in terms of L. You can check. Just by computation that this gamma fg, I can express it just in terms of the generator. It's just L of the product fg minus f of f times Lg minus g times Lf. And there is this 1/2. Okay, just do the computation, it works. Okay, so if L was just a first order differential operator, then because of the Leibniz rule, this would be 0. Right? So you can view this gamma as quantifying how far your generator is from being a first order differential operator. The nice thing with this definition is that you can extend it to any space, right? The sum there is really for discrete spaces, but this makes sense on any space. You give me any generator, I can define this. And so in particular, you can compute this for diffusions, for example. Okay. Okay, so let me introduce a definition now. It's an iterated version of this. So it looks complicated, but don't worry, we are not going to use this very much. But there is a way to iterate this formula, right? If you replace every product that you see in this formula, so this, maybe I should explicitate, putting colors whenever you see a product. So this is product of f and g, this is product of f and ng, and this is product of g and lf. Okay, a product is a bilinear form it's linear in both arguments, right? And this gamma is also a linear form in both in the two arguments. Right? Now this iterated gamma operator is defined by just replacing every product that you see here by this gamma. Okay, so it's a bit weird to do that, but let's do that. So gamma 2 of fg. Right, so replace whenever, use the same formula here, but replace every product by the gamma. Okay, so you have L of a product, so now it's L of gamma. Then you have the product of f and Lg, so it becomes gamma of f and Lg. And then you have the product of g and Lf, so it becomes gamma of g and Lf. Okay, there is no reason to do that, I agree with you, but it's just a definition. Okay, and now I can state a theorem, or maybe a lemma. So for any real number ρ, and ρ will be my curvature, the following are equivalent. Okay, I'm going to list 3 different properties. The most interesting one maybe is the last one, so I'm going to start with that. That's the one we are going to use for cutoff. Again, this theory was invented 40 years ago, nothing to do with cutoff. But for me, this is the formulation that will matter. So this formula is called local Poincaré for good reasons. But let me state what it says. So you have this local Poincaré inequality for your Markov chain. So you take a Markov chain with this generator L, and then you have an estimate on the variance of any function at any time t, starting from any initial state x. Okay. And this local Poincaré tells you that this variance is at most a certain constant, which has an integral form. So 2 exponential minus 2 rho s ds. So that's just a constant, right? And then times expectation of this carré du champ at time t. Okay, so it's just a way to estimate the variance of a function. It's useful. You know, think of your favorite model of Markov chain. The first thing you want to understand is the expectation at your favorite time. The second thing you want to understand is the variance. This is a good way to understand, to compute the variance or estimate the variance of your Markov chain at any time t. Okay, so think of this as the property you really want. And now the other 2 properties are characterization of this, because this is rather complicated to establish just like that. Fortunately, we have simple characterization. So the main criterion here is called the CD rho infinity criterion. So it's a very simple way to check this, and it's equivalent to this, and it's in terms of this gamma 2 operator. So it tells you that gamma 2 of f should be larger than rho times gamma of f for every f. This also is for every f, for every t, for every x. Okay. So it's a very compact and simple way to check this complicated condition, but really what you want is this, and this is the way to prove this. What? Why is the infinity? Why is there an infinity? Because there is a more general condition with this, where this is another parameter, and when you specialize to infinity, you get this. Okay. I'm not going to look at the. Yes. So C and D is for curvature and dimension. This is curvature and this is dimension, but in our case, dimension is infinity. Okay.
And why you write the integral in the constant?
Yeah, good. I could have computed this integral. I'm good enough to compute this. The problem is that when rho equals to 0, you get a formula that is not well defined. This makes sense for any rho, so I don't care. Okay, but yeah, you're right. Yeah. You can always approximate this by a finite sum.
Last condition, the expectation and variances are with respect to the law at time t.
Yes, that's your Markov chain at time t. You can start from any place, provided this is deterministic, right? Because when you take t equals 0, you see this integral is 0, so your variance has to be 0. So you cannot start from something random, but as long as you start from a deterministic state, any state, you have this nice formula. Okay, and I will explain why it's called local Poincaré in a minute. Okay, and the second property is a bit in between. This is static, there is no time. This, there is time and variances and expectation. And this is something in between the two. It's called the subcommutation relation. And it's simply something that says that when you apply gamma, and then you apply pt to any function f, it's always at most the same thing when you interchange the two. Right, so if it were an equality, it would be commutation relation. It's subcommutation because you lose a bit. And what you lose is just exponential of minus 2 rho t. Okay? Again, for every t, for every f. Okay, so why is this called, I'm going to prove this lemma, it's easy. Why is this called a local Poincaré? So let me make this more precise in this remark. Suppose that rho is strictly positive, right? Rho could be negative. Rho is my curvature, right? It will be called curvature. And so it can be negative, just like for manifolds. But when it's strictly positive, then you can compute this. Massimiliano can compute this. And then you can take t to infinity in this. So let me call this property star. To obtain the following. So it's a good exercise for you. What happens here when t tends to infinity? What do you get in the limit? First, just this term. Yes? My chain is irreducible, so as t tends to infinity, this converges to the stationary measure, regardless of where you start from. So what you get here is just the variance under the stationary measure. Maybe I should make this precise by putting a pi of f. Right? Okay, on the right-hand side, you have this infinite integral from 0 to infinity, which is 1 over rho, right? Okay, and then what is this? Same as here, right? T tends to infinity, so you get the stationary measure. So you get expectation of gamma of f. But remember, expectation of gamma of f when f is equal to g, right? It's just the Dirichlet form. What's the name of this inequality? Nobody knows. It's Poincaré, of course. we recover exactly the Poincaré inequality. Right, so in particular, this tells you that you have a relation between this rho and the Poincaré constant. The Poincaré constant, this gamma optimum, is always at least rho. Of course, when rho is negative, this doesn't tell you anything. But when rho is positive, it gives you a bound on the Poincaré constant. Okay, so it's called local Poincaré because Poincaré is an inequality for the stationary measure. And this inequality is the same, but now it's the distribution of your chain at time t, any t, instead of just at stationary t. So it's much stronger. It's true at any time. Right? It's good to be able to compute variances under the stationary measure, but it's much better to be able to compute variances at any time on your chain. Right? So that's the term local is here is not for the local in the sense of space, but local in the sense of time. Right? It's true at any finite time. Okay? And it's not surprising, right? We started by saying that this gamma is a local version of the Dirichlet form. So when you write this condition for gamma, you get a local version of the Poincaré inequality. Okay? Okay, so let me prove the lemma. It's very easy. So the only thing to realize is that this variance, right? You write it. Variance is a second moment minus the square of the first moment. So variance of this is just expectation of this minus expectation of this squared. Right, so in terms of PT, this is just PTF square applied to x. And then this is PTF of x square. Okay? Now I can write it as follows. I can both terms here PT of f square. So what I want to understand now is PT of f square, forget about the x, minus PT of f square. And I can write this as follows. I just realized that this is really PS of PT minus S of f square, evaluated at S is equal to T. Right? When you take S equals T, you get this because P0 is the identity. And this is the same expression, but now evaluated at S equals 0. So in fact, this difference it's just the difference of, it's a function evaluated at time t minus the same function evaluated at 0, so it's equal to the integral of the derivative of this. Right? So if I call, so it's this, d over ds of this quantity. Okay, this is a pointwise equality between functions. You should evaluate this at every point x, and you have an equality between numbers. Okay, so let's compute this derivative. It's just one line, so I'll let you do it, but okay, it's easy to differentiate PT. You know, when you differentiate PT, you get L times PT or PT times L. So just basic computation here gives you that this is PS gamma PT minus S of F. Okay? So we obtain this nice expression for the variance, which will be useful. This does not use any of those properties, the general formula for the variance of a function. You can write it in integral form as just this. There is a 2 Okay. Okay, and now I can prove the lemma because so assume that you have this. So if you have 2, then you can use the subcommutation property to exchange the 2, and you get that it's less than integral from 0 to t. You get 2. PS times pt minus s is just pt. Right? And then gamma of f. And then there is, you pay an exponential. The exponential is this, minus 2 rho t minus s. Yes. Okay, so this is really exactly integral from 0 to t. Right, times pt gamma f. And this is exactly this. So what we just showed is that 2 implies 3. Okay. You just evaluate this inequality at a point x, and you get this. Okay, maybe I should keep the statement here. So let me now prove that 1 implies 2. To prove that 1 implies 2, I need this complicated gamma 2 operator. But let me start here. And you realize that here also there is a product, right? There is a pt minus s f times itself. So this is a product. Now I replace every product by the gamma. And so here I will get a gamma 2. And so what you get is so you replace this product operation with the gamma operation. Everything is bilinear, so the rules for differentiating are the same formally. Right? So if I replace multiplication by gamma in this formula here, what I get is that derivative of ps, and now instead of the square, I have gamma of pt minus s. F. And on the right-hand side, I get the gamma 2 instead of the gamma. Okay, and now you apply this CD criterion. So this by property 1 is at least 2 rho times ps gamma pt minus s. Okay. So if I call this function f of s, what I get is that the derivative of s is at least 2 rho times f. Okay, and so you can integrate and you get that f of t is at least exponential 2 rho t times f of f0. And when you replace the f by its value, you get exactly 2. Right? Because f of t is pt gamma f, and f of 0 is gamma ptf. Right? So very clever, but that's the. So this proves 1 implies 2. I won't prove the last implication because we don't really use it, right? Remember, that's the property we want to use for Markov chains. And it's too complicated to prove, so we use this as a simplification. So we only need this implication in this direction. We don't really need this one. Right? The implication 3 to 1 only tells you that by looking at this, you are not losing too much. But it's easy. It's just you take to get from here to there. Just look at the second order Taylor expansion at time t equals 0, and you get this. Okay, I won't do that, but that's it. Okay. So we'll give you examples of where you can compute this curvature. But before that, maybe I should explain to you why is this notion useful. So maybe here is the definition. The Bakry-Emery curvature of the chain is the largest constant such that those properties, any one you want, they are equivalent. Okay? Now it's not clear at this point that this has any relation with the Ricci curvature, but it has, and we'll see this on concrete examples. For the moment, just think of it as a simple property which is easy to check on concrete models because of this static property, right? It's just a matter of computing things at every state. And I will give you a lot of examples, but think of rho as something you can easily compute on models. What's the interest of this? Again, for cutoff, we'll use this very strongly. But this is not the way curvature was used. The main use of this definition is contained in the following theorem. So that's maybe the most famous result in the Bakry-Emery theory of curvature. I'm going to call this the Bakry-Emery theorem because for me it's really the cornerstone result in the theory. That explains why this notion is useful. So here is the theorem. Again, this started 40 years ago, the 80s. So if you look at diffusions, this notion was invented for diffusions. And the theorem tells you that if you know the Bakry-Emery curvature, then you understand log Sobolev, which is this very strong functional inequality, the strongest we have seen, the one that controls hypercontractivity. So this optimal log Sobolev constant is at least the curvature divided by 2. Okay, that's a very powerful statement. Because remember, this functional inequality is quite hard to understand on concrete models. This rho is easy to compute. And you get this for free for diffusions. Okay? So it's restricted to diffusions because of the chain rule. Right? This result strongly uses the chain rule. So maybe let me give you a proof of this. So for the proof, I will need one lemma. And the lemma, you'll see, so the goal will be to generalize this to discrete chains, of course. Right? Whatever is true for diffusion remains true in the discrete. But for that, I need to be sure that this lemma also applies for discrete chains. So here is the lemma. So discrete or a diffusion. You have this inequality for the Dirichlet form. So maybe with a square it will be easier. So squared, and this is at most square root of f times the expectation of f gamma j. Okay, and this is true for any positive function f and for any g. Okay, so here is the proof, and then we'll see how this implies the Bakry-Emery theorem. So I'm going to do the proof in discrete. If you want the result for diffusion, just replace every sum by integrals. So by reversibility, I can use this symmetric form of the Dirichlet form. So pi x txy, and then difference of values of f and difference of values of y. Right? This is true when your chain is reversible. And then I'm going to write this as square root of f minus square root of f times square root of f plus square root of f. Right? So this is really right? Okay. And I'm going to do another thing, which is that because this quantity is symmetric by reversibility. Here, no. No, here, no. Not yet. It will come. We'll apply Cauchy-Schwarz at some point. Yes. So this is symmetric in x and y by reversibility. So instead of having the contribution from x plus the contribution from y, I can ignore this term and remove the 1/2, and that's the same. Okay. So what I get is sum over all xy, pi x txy, then square root of f of x, and then the difference is so square root of f of y minus square root of f of x, and then g of y minus g of x. Okay, and this I can rewrite it in terms of the gamma operator, so it's really twice the expectation under pi. I have square root of f, and then what remains is really gamma applied to square root of f and g. Okay, and then I simply apply Cauchy-Schwarz there. Actually, I'm going to apply Cauchy-Schwarz to two different symmetric bilinear forms. Right? I'm going to apply Cauchy-Schwarz to this expectation, so to the scalar product in L2 of pi. Right? That's the usual Cauchy-Schwarz, you know. But I can also apply Cauchy-Schwarz to this gamma, because this is a symmetric bilinear form. Right? So by Cauchy-Schwarz, you know that this gamma of square root of f and g is at most square root of gamma of square root of f and gamma of g. Okay, just because it's a bilinear form in a symmetric bilinear form in its two arguments, it satisfies Cauchy-Schwarz. Okay, so I'm going to use this inside the expectation and then apply a second Cauchy-Schwarz to this expectation. Okay, so those are two applications of Cauchy-Schwarz, but not to the same object. And you get now that the square of this is at most 4 times expectation of something times expectation of something. Okay, so Cauchy-Schwarz is used to break this expectation into two parts. But first, I apply this. In one of the expectations, I'm going to just put this gamma square root of f. And in the other expectation, I'm going to put this gamma g and this f. And that's it. Right? That's exactly what I wanted. Okay, so just Cauchy-Schwarz. And now I can prove the theorem. Okay, I want to prove a log Sobolev inequality. So what I need to prove is that the entropy of f is at most, and I'm going to do a very long computation. And in the end, I would like log Sobolev inequality. Or maybe I should write the goal. That the entropy of F is at most rho over 2, 2 over rho, times this. Right? That would be the log Sobolev inequality with this constant. Okay, so how am I going to prove that? I'm going to write the entropy as an integral. The entropy is integral from 0 to infinity of the derivative of entropy of PTF. Right? With a minus. So why is that? Simply because if you compute this quantity at time t equals infinity, PT of F is constant, so the entropy is 0. And at time t equals 0, it's exactly this. Right? So again, a function is the integral of its derivative, and you get this. Okay, but we computed this. Right? We know what this is, the Fisher information that we computed when we studied the decay rate of entropy. This is really PTF log PTF dt. Okay, now by reversibility, I can move this PT on the other side. Okay, and what I claim is that what is inside the integral is at most what I would like here. So times 4 exponential of minus 2 rho t. Right? If I can prove that, then by integrating this from t equals 0 to t equals infinity, I get exactly this. Okay, and then I'm going to use this to estimate this. Of course, to apply the lemma, I take G to be this, right? This is my G. So we know that the square of this quantity is at most 4 times, and I'm happy with this 4 because it's here. So 4 times exactly this. So this is nice. It starts very close to what I want, and then there is this expectation. So expectation under pi of f and gamma pt log ptf. Okay, I haven't used the assumption so far, but I have this subcommutation property. So whenever you see gamma pt, just interchange and get an exponential. Okay. So now I'm very happy because it's really exactly what I want. And then those are exchanged, so now I get expectation of under pi of f times pt gamma. Okay? This you can write it as a scalar product. It's the scalar product of f with this, right? But then pt is reversible, so I can put pt on the other side of the scalar product. Okay, so just again by reversibility, this is the same as square root of f, and then expectation under pi, and I get ptf times gamma log PTF. Okay, and here comes the miracle, because we have not used the fact that we have a diffusion yet. Right? Remember, the Bakry-Emery theorem only works for diffusion. So now I'm going to use the chain rule. So because of the chain rule, this as a simple formula. So remember, the chain rule is a way to compute the derivative of a composition of a function. For diffusion, this gamma is a differential operator, so you have rules to compute gamma of a function of f in terms of gamma of the function itself. So it turns out that when you do this, by the chain rule, here what you get is exactly, so maybe I should write it, chain rule, for diffusions only, gamma of log of any function is the same as LH divided by h minus L of log h. Right? That's a miracle that comes from the Leibniz rule for differentiating the composition of two functions. Okay, so here you have gamma of log of something, so you get this. And you see you are dividing by h, and h is this function here. So here this simplifies a bit, and what you get in the end is just precisely the Dirichlet form of PTF and log PTF. Okay? So again, I can put this h, I can multiply by h through, and I get LH minus h times this. When you take expectation of LH, it's 0, because L is because pi is stationary. And so only these terms remain, and this is exactly this. Okay, so you have this miracle in the end, but apart from that, I'm done. Why am I done? You see, I have this quantity, and this is the same quantity. Remember, you can put the PT here or on the other side, it's the same. And you see, so I have a square, I can simplify by this. I can simplify the square and simplify this term. And what remains is what I wanted. Okay, so it's a miracle, but it works. Okay. So I would never have found this proof by myself, of course, but now that the proof is done, I can prove a discrete version of it very easily. So this is classical 40 years ago. The theorem I'm going to write is last March.
Sorry, what is the minus one?
The minus where?
When you do the chain rule, you have minus.
Yes, but in the definition of the Dirichlet form, it's f scalar product with minus Lg. There's a minus L in the Dirichlet form. So it's a discrete Bakry-Emery theorem, if you want. So before this theorem, the Bakry-Emery theory of curvature was not really used in the discrete because it was useless. And this theorem makes it more interesting. So for any reversible chain, remember whatever is true for diffusion due to the chain rule remains true for the discrete. There is a discrete version of it where you pay log of d. So you still have a control on the log Sobolev constant of your discrete chain, which is this very strong hypercontractivity property. And then you are going to, it's essentially rho, but you lose universal constant and then log d. Where I remind you that d is the maximum degree in your chain. Or more generally, look at the smallest positive entry of your transition matrix and take 1 over this. Okay, so for random walk on bounded degree graphs, for example, you have exactly the same. So d is constant for bounded degree graphs. You have exactly the same result as in the Bakry-Emery curvature. Okay. And there is almost nothing to prove. You take exactly the same proof as before. The only place where we used the diffusion was this chain rule. So what I need is an approximate version of this for discrete chains. Okay. And this, I'm doing it because we are going to use it for cutoff as well. So it's a simple lemma, a two-line lemma. and then this complicated proof by Bakri-Emery. So all we need is this lemma to replace the chain rule. Okay, so that's the second time already that we see this idea. That for any discrete chain, you still have a version of this identity here. This was an equality. Maybe I'm going to write it like that. Gamma of log of any function. So the chain rule would be exactly that this is this minus this. This is not true in the discrete world because you cannot compute the derivative of the composition of two functions easily in the discrete. Right? But it's approximatively true in the sense that it's at most this time an error, which I'm going to explicitate, and it's at least the same quantity times an error, which I'm going to explicitate. So it's bounded between, it's almost the identity except for this factor, and this factor you can take it to be 1 in the case of diffusions. Okay. So what is this phi? It's a linear function of r, right? It's like r squared over 2 times r plus exponential minus r minus 1. But you know, when r is large, it's just r over 2. So it's certainly always at most 1 plus r. So think of it as a correction term, right? The price that you have to pay to repair the chain rule. What is r? It's, as before, it's the regularity of the log Lipschitz constant of f. So we have already seen this idea before. You can repair the chain rule provided you are looking at functions that are smooth enough in the sense that they don't jump too much when you make a transition of your chain. And then you get an approximate chain rule. Right, so you can view this. I did not prove this. It's usually done by using the Leibniz rule. Right? But this is actually a proof of this because you can take, right, you are in the diffusion setting, you are doing steps that are more and more infinitesimal. So the price that you pay, the difference between the value before the jump and after the jump becomes as close as to 1 to 0. Right? So r becomes 0. And then when r is equal to 0, this is really 1 and 1. So you get, it's a very weird way of proving this, but that's a way to prove this. Okay. So what's the proof? It's really 2 lines. The only thing to realize is that this function phi is increasing. Easy to check. So if you take two neighbors x and y, we know that the value of phi of this, right? So it's at most the largest value of this, which is phi of r, and it's at least the smallest value, which is this. Right? Just because by the definition of this. Right? Remember, this is the maximum over all neighboring states of this with absolute values. Right? So I get this. Okay, so now you replace by the definition. So what you get is 1/2 log square of this is less, and it's at least and at most. Okay, here the two terms will be the same. So I'm going to compute only this one. So what you get is this term when you replace r by this. So it's this times log of f of x over f of y plus f of y over f of x and minus 1. Right? I just put this term on this side. Okay, this is true for any neighbor. Now I multiply by txy and the sum over all y's to get the result. So you multiply through by txy and you sum over all y's. Right, what you get here is precisely the gamma of log f, right, which is this. And what you get when you sum this is precisely this expression. Okay. Okay, so it's an approximate chain rule. The problem is that, remember, we want to prove a log Sobolev inequality. So it's a functional inequality. The way we proved it, the Bakry-Emery proof, you start from any function f and you try to conclude that indeed you have this. That's what we showed. And this was for every function because that's what you need for a log Sobolev inequality. So at some point we use the chain rule. We can always replace the chain rule by paying this phi of log Lipschitz of f. But you want this to be true for every f. And for every f, I mean, this can be made arbitrarily large as you want. Right? So it seems like a problem here. But remember, you have learned this from the previous lectures. You don't really need to establish this for every f. It's enough to prove it for the function f that achieves this equality. And we saw that this one satisfied that this is a constant times log d. So that's it. Okay? You prove it just for this one, and that's enough. For the one that realized this inequality. And this one, we know its regularity, because remember, if you want the extremizer of this log Sobolev inequality has to solve a particular equation, and from that we deduce this. Right? So you just replace, you repeat the proof of Bakry and Emery, except that at some point, instead of a nice equality, the last step with the chain rule, you pay this phi of r, but r is equal to this. You pay phi of r, but remember, phi of r is at most 1 plus r, so you pay 1 plus log d. And that's where you get this.
You need this control over pt of f.
Great, so great remark. So in fact, we need to apply this chain rule not only to f, but to ptf. Turns out that it's even better. The regularity of log ptf is even better than the regularity of f. I have a one-line lemma in the notes. You're right. But that's essentially it, right? There is no new idea in this proof. Okay, so now I want to convince you that this is a useful theory. So I would like to give you as many examples as possible of chains that have this non-negative Bakry-Emery curvature to prepare for tomorrow, where we study cutoff with this notion. So by examples, I mean examples of chains whose Bakry-Emery curvature is nice. So for me, for cutoff, I will only need non-negative. But for the Bakry-Emery theorem, you need positive. You need a value for rho. Right? Okay, so let me start with the historical example, the case of diffusions. So remember, we always have this Langevin diffusion. The xt is minus the gradient of potential plus square root of 2 dBt. Right, the stationary measure is right. We wrote the generator for this. It's just the Laplacian applied to f minus gradient of u scalar product with gradient of f. Then you can compute the gamma operator, just the norm of the gradient squared. Okay. So that's why you have this nice chain rule, right? When you apply this to gamma, when you try to compute gamma of log of f, you can use the chain rule to compute this, and that's what essentially that's where it comes from, that you have equality between this and this in the world of diffusion. Okay, then you can compute the gamma 2 operator from this. When you compute it, you have two terms, one with which you cannot do much, but it's non-negative, so it's good for you. So it's the Hessian of f, computed in this Hilbert-Schmidt norm. And the second term is related to the Hessian of u. It's just you compute gradient of f against the Hessian of u, like that. Okay? So if you want, remember, we want to compare this to, if you want to compute the curvature, the first criterion was just this, that you want gamma 2 of f to be larger than rho times gamma of f. Right? Gamma of f is this, so you are just looking for a bond on this Hessian in terms of the norm of the gradient, so that's convexity. It's just that the Hessian of u, you want it to be larger than rho times the identity. Okay, so I'm hiding something under the table here. It's certainly true that if you have this, then you have this, and that's enough for us. But you still have this term, so maybe you could think that this, you can use this, the non-negativity of this to improve this. In fact, no, there is no way to use this in this inequality. So it's really an equivalence. But all we need is this direction. So you see the curvature dimension condition is just a condition on the convexity of your potential. If your potential is convex, the curvature is non-negative. And from this, we get this nice log Sobolev inequality. Okay, the nice thing is that this generalizes to manifolds. And you start to know me, so you probably realize that I don't understand anything of what I'm going to say now. But you can make sense of this diffusion of this equation on any manifold. There is a way to define this Brownian motion. Right? There is a way to define a gradient. Everything works through. Here, this delta is, of course, the Laplace-Beltrami operator of your manifold. Right? You do the computation. I have no idea what this means. But what you get in the end is that this is the same as saying that, and when you compute the gamma 2, you get an additional term. So that can actually help you in getting some curvature. So you still want the Hessian of u, but then you get the Ricci curvature at this point for your manifold, and you want this to be larger than rho times the identity. Okay, so what does this mean? If you are looking at this diffusion on a manifold that has non-negative curvature or positive curvature, then this term will help you in getting the CD condition satisfied. Right? So in particular, you can look at just at a simple object, which is Brownian motion on your favorite manifold. Brownian motion on a compact manifold. So Brownian motion corresponds to the case you see here where you don't have this term. It's just Brownian motion. So u is 0. And so what you get is that the curvature of your Brownian motion is exactly the Ricci curvature being larger than rho. Right? So this Bakry-Emery theory of curvature, when you apply it to Brownian motion on a manifold, you get the original definition of curvature for your manifold. Right? So it really, it's a satisfying notion in this sense. Right?
Rho times the metric.
Yes, right. So it's normally it's Ricci of the metric at this point. So yes, but here it's really this Ricci curvature in the sense the minimum value. I mean, you define the Ricci curvature of your manifold as the smallest value such that this holds, and then you get exactly the function. Okay. So that explains the success of this Bakry-Emery theory for the continuous. But let's look at discrete example now, just to see if there is anything interesting. So a large class of examples of nice discrete chains are random walks on groups. On finite groups. Okay, so to define this, I need a group, of course. And then I need simply a way to generate random elements from my group. So you give me any probability measure you want. And I will use this measure to sample elements from the group in an IID way. And then my random walk is simply, whenever my clock rings, I multiply my element by this random sample from nu. Okay? So in terms of transition metric, what happens is that the chance that I move from x to y when my clock rings is simply the chance that I pick up the right element. And what is the element that when you multiply on the left by this element, starting from x, you get y? Well, it's exactly nu of y x inverse. Right? So that's a simple transition matrix. Right? And here is this nice fact for Bakry-Emery curvature. Easy to do, right? Just compute the gamma 2 for this. It's a bit long, but it's done in the note. So if nu is nice, and it means that it commutes. So nu of xy is equal to nu of yx for every x and y. If nu has this nice property, then the Bakry-Emery curvature is non-negative. Okay, nice. So in terms of implication for log Sobolev, this is useless. But for cutoff, this will be enough for me. Right? So any random walk that satisfies this property works. So this property, if your group is abelian, this is trivial. This is true for any measure nu. Right? If your group is abelian. If your group is not abelian still, this you can rewrite it. Sometimes people write it like that. It's the same as saying that nu is conjugate invariant. So it means that this is equal to this for any x and z. And so one non-abelian example, take the group of permutations. And the elements that I draw at random at every step are just random transpositions. It's a famous random walk for which a cutoff has been proved using representation theory. Right? So in this case, nu is simply the uniform measure on the set of transpositions. And the set of transposition is conjugacy invariant. It's a conjugacy class. So you have this identity, even though your group is not abelian. Right? So there are many nice walks which satisfy this. Abelian, of course, but any random walk which is conjugacy invariant satisfies this. Okay, so we can go a bit further, actually, and this will be useful for my two toy models. Maybe just an example. Random walk on the n cycle. Is non-negatively curved simply because it's an example of an abelian random walk. Okay. Now we can, of course, this also works for the hypercube. The hypercube, you can also view this as random walk on an abelian graph, but for the hypercube, you can do better. So this was fact 1. There is fact 2. Same proof, actually, but just a twist in the end. So if in addition to this property, your measure nu is supported on element which has self-inverse, self-inverse element, so meaning that Z inverse is equal to Z. Right? Then you actually have a positive bound on the curvature. Where ρ is now the minimum non-zero value of your measure. Okay, so it looks a bit complicated, but okay, simple example, random walk on the hypercube. Okay, so the n cube is -1 plus 1 to the n. It's an abelian group. So this is satisfied for free. And moreover, in this group, every element is its own inverse. Every element has order 2. So in fact, any random walk that you could define on the n cube satisfies this condition and this condition that it's supported on self-inverse element. So in particular, for my special case of simple random walk on the n cube, what's the minimum value of nu? Remember, nu is 1 over n for every possible coordinate flip. So in the end, you get that rho is at least 1 over I think there was a 2. Yes, there is a 2 missing. It's 2 over n. Okay, so you get a positive bond on the curvature. How good is that? Well, I don't know if you remember, but this is actually the spectral gap. Right? And we saw that it's always true that rho is at most the spectral gap. So in fact, there is equality. So it's exactly the right value. Okay, so just to convince you that this is a curvature is something that you can easily compute on models. One last model, which is even more convincing, is Monte Carlo Markov chain, right? If you want to claim that your theory is tractable, you have to be able to compute it on for Monte Carlo Markov chains, which are really real-world Markov chains, right? So example 4 is MCMC. So let's take a simple setting. You take x to be -1, 1. And we are going to look at those dynamics. So you have a measure. And this is your target measure. You are trying to sample from this target measure pi, which is complicated. And the way you do that is by doing flips. So whenever you clock ring, you choose a coordinate uniformly at random and you flip it. Okay. So this xi is the state obtained when you flip the hive coordinate. Again, if you do this, you will not sample from pi, you will sample from the uniform measure. So you have to adjust the rate here so that this is the measure that you get. So this is some rate that depends on I and x. And we have seen many choices. Right? Let me remind you. Depending on your taste, you can take this. This was a Glauber. Right? You can take this. You want something that ensures that it's reversible. Right? This is Metropolis. And the last one, I don't know the name, but okay, so those are examples of choices. Okay, so what's the curvature for this? Well, at least in one special case, I know the answer because when you take pi to be uniform, then this walk is exactly your this example here, and we know that rho is non-negative. Right? So it turns out that this remains true as long as pi is close to being a product measure. So it's a nice fact. There is a paper by Pedrotti on that. In fact, it's even quantitative. You have a bond on rho, and rho is essentially of this order 1 over n. But for cutoff, I will only need this. As soon as pi is close to being a product measure. So what do I mean? So there is a precise statement, of course, and the statement is the following. I'm going to write a formula and then explain. Positive part is at most ci of xi. And you want this to be true for every I, every j, every x. Okay, so what does it mean? Maybe just to make sure. if you have a product measure, then this quantity will be 0. Right? Because this quantity, if you look at this CIX depends on the marginal, it's essentially the marginal law of the hive coordinate under the stationary measure, given everything else, given that everything else is at x. Okay? So here you are saying, what's the marginal law of j given everything else, and what's the marginal law of the same j when you change another coordinate somewhere? If this is product, then the marginal law doesn't change, and this is 0. More generally, if you look at your favorite spin system on a graph, this will be 0 unless I and j are neighbor, because if they do not interact, then changing the flips very far away will not change the conditional marginal. Right? So it's 0 for product measure. It's also 0 whenever I and j are not neighbors in your spin system. Okay? And so this gives you a quantitative bond, so maybe it's good to give you examples. When is this satisfied? Let's look at the Ising model on the graph.
Can you have a constant or no? No. You need a constant.
A constant in this inequality? No, you really want this. But you know, when you put, for example, for this particular form, when you put this here, you really get something about the correlation of I and j. So it's really a natural thing to do. It's really this correlation matrix of your spin system that shows up. So it's a natural condition to expect. Maybe a convincing example is Ising model on the graph. Right, this is just the case where pi of x is proportional, so the constant is complicated to compute, times beta, and you sum over all edges in your graph, xi times xj. Right? So this is the famous Ising model on your graph. And in that case, this will be satisfied as soon as beta, your temperature, or inverse temperature, is at most, so beta times delta is at most a universal constant. So this is a universal constant, like 1/2 or something like that, 0.44. And delta here is the maximum degree in your graph. Right? It's actually not surprising that this maximum degree appears, because you see in this sum you are counting all the sites that have an influence of the site I, and in those spin systems the sites that influence I are just the neighbors of I. So you need a bound on how many of them you have, and that's it. Okay. So that's it for examples. Or maybe if you, how many of you know about the hardcore model? That's not enough for the hardcore model. So you put particles on a graph, but they don't want to be neighbors. So independent sets. But I'm not sure you are interested enough for me to. But there is a simple criterion like that for the hardcore as well. So take your favorite model, and as long as the temperature is small enough or large enough, you will get a non-negative curvature. So again, it's really an effective theory. Okay, I would like to end with a conjecture. That's for you guys. So we have seen two notions of curvature. One was this Olivier-Ricci curvature, and the other is this Bakry-Emery curvature, and they have a lot of similarities. So K1 has many similarities. With the Bakry-Emery curvature. Rho. So here are a few things that they share. both control the spectral gap. That's what we saw. Right? Both control entropy as well. Right? In one case, it was this Perez-Tetali conjecture, which was false but could be repaired at the price of looking at reasonable chains. And for Bakry-Emery, it's this Bakry-Emery theorem that it controls log Sobolev. And also both give and that's what I'm going to use, the only thing I'm going to use for cutoff, both provide local Poincaré. Maybe I should explain that because for Bakry-Emery it's clear, but for Olivier Ricci we never saw those local Poincaré, so let me explain. Remember, we had this nice integral formula for the variance. And from this, you immediately get a local Poincaré inequality. So the variance of f was just PTF squared minus PT of f squared. And we saw that this could write it as an integral. This integral, which I cannot compute. And then times no, that was, sorry. That was 2 PS gamma PT minus S F. General formula for the variance, right? And then we use Bakry-Emery to interchange the two. But if instead of Bakry-Emery you have Olivier Ricci, you can still write something because, so remember, if you look at the definition of gamma of F, it's still on the board here. This is at most the Lipschitz constant of F. Right? It's a very crude bound, but you can always do that. So it's true for any x. Okay, so then you apply this in particular to gamma pt minus s f because you want to compute this. And remember, Olivier Ricci controls how much this decay with time. Okay. This was this dual formulation of Bakry-Emery curvature in terms of Lipschitz norm. Okay, and then you apply, you insert this here, and what you get, using the Olivier Ricci curvature instead of Bakry-Emery, is a weak form of this local Poincaré inequality. So what you get is that the variance of f of xt is at most same as in Bakry-Emery, this integral. But then instead of having the expected carré du champ, I get this uniform Lipschitz square norm. Yes, there is one half here. Yeah. Ah, yes.
There is a kappa 1, no? So
K1 is here. Yes, sorry. So it's K1. And then times this. Okay? So this, of course, before instead of this, before in the Bakry-Emery world, we had this. Okay? So this is always larger than this, but it's still a local Poincaré, a weak local Poincaré, and that's all we need for cutoff. Okay, but you see, it's again one similarity between the two, and it's really a similarity because you can interpret this, at least this, you can view this as a sort of Lipschitz norm. Right? It looks very much like the square of a Lipschitz norm. And so, yes, those two notions seem very connected. Okay, so here is the conjecture for you. So in all examples I know where Bakry-Emery curvature is non-negative, also Olivier Ricci is non-negative. And in terms of consequences, everything that is true for Bakry-Emery is also true for Olivier Ricci. So here is the conjecture. It's personal, so I have nothing, nobody to blame if it's wrong. Yeah, exactly. I'm going to say that. So is it true that you have this? Okay, so I don't want to say a false thing because I'm recorded. So let me add a few additional things so that it's true. Maybe up to universal constant. Also, remember that this Olivier-Ricci curvature depends on the choice of a metric. You can choose the metric as you want. So presumably the one that we use, right? The number of steps that you need to make in order to connect two states, but maybe some other one. And just to be sure, for reasonable change. This I have learned from the masters. Okay, so that's for you, but they seem really, really connected. Those are two notions of curvature that seem very, very similar. There is a third notion of curvature that maybe you have heard of, which is this entropic curvature. It's much more complicated, and so far I don't know how to relate it to the other ones, but you can ask the same question, I guess. Okay, so is there any question on what I said? Yes? This is?
the side of inequality.
So it's actually the good question. Yeah. No. What I mean is this seems always stronger than this. Right? Look at the Poincaré inequality. This local Poincaré is stronger. With this, it's better than with this. So Bakry-Emery seems always stronger. It controls log Sobolev instead of modified log Sobolev. So it seems always a bit stronger. But I have no proof of this.
Sorry, is there any consequence if they were equal?
No, I guess it would just, okay, maybe, no, maybe, you see, in concrete models, how do you prove bounds on this? Just by coupling, you take two trajectories, you try to, I find it easier than computing this gamma 2 operator. So in that sense, it would be nice to connect the two, to prove equality between the two would be very nice for that. But I guess other than that, it would be more satisfying because so far we have several notions of curvature and they are not connected. We would like to say that there is a notion of curvature, a right notion of curvature.
No, but I wanted to say if they're equal rigidity. If they're equal, you can say something about the underlying chain.
Good question. This I don't know. Okay, no, yes, that's a good question. Understand what happens when you have precise equality. I don't know. Yeah. Okay, so again, you have seen many tools, functional inequalities and curvature. They were used before to study mixing times, but they will produce bounds that are, at best, give you the right order of magnitude, but never the right constant. And so we are not going to use them in the way I presented. But we are going to use many things that I presented, including this approximate chain rule, the fact that you have this local Poincaré, and this will be enough to prove cutoff. Okay, but it's a different use of those classical notions, I would say. So now you know all I know about mixing times, and we can start developing this theory of cutoff starting tomorrow. Okay, so I'm done.